Lecture 2.6, Length Contraction. In the last lecture, we used Einstein's postulate that the speed of light is constant for everyone to derive an expression for time dilation. We used a vertical light clock moving horizontally in the derivation. In this lecture, we will use a horizontal light clock in relative motion to derive an expression for length contraction. Consider a light clock oriented so that the light ray bounces back and forth horizontally. The distance between the mirrors is L0, and the time for one round trip for the light ray is delta T0 equals 2 L0 over C. Let's now observe the light clock from a reference frame moving horizontally with velocity v. We'll assume the distance between the mirrors as measured from the moving reference frame is L rather than L0. It's the relationship between L and L0 that we are trying to solve for. So let's break the motion down into parts. So let's mark where the initial pair of mirrors is. So the left mirror is here, and the right mirror is there. So let's run the simulation forward in time, and we see that the right mirror has moved here. So we're going to call the distance between the pair of mirrors from the moving reference frame L. And then this extra distance is going to be V times T1. So T1 will be the time it takes for the light to bounce from the left mirror to the right mirror. So the total distance that the light ray moves in time T1 is L plus V T1. And that is equal to C T1, assuming that the light ray moves at the speed of light over this time. So we can solve for T1. To find that T1 equals L over C minus V. So let's remember that result. We'll move it over here. So now we'll mark the left and the right mirrors at time T1. And we're remembering that this distance is again going to be L. And now we're going to run the simulation forward in time again until the light ray now hits the left mirror. So it will complete one tick of the clock. So now this is where the left mirror is when the light ray reaches the left mirror. So this distance here will be the velocity of the light clock, v, times time, t2. So again, we can write down an expression for the total distance that the light ray has moved in time t2. So that's going to be the distance between the two mirrors, L, minus VT2. And again, this will equal C T2, assuming that the light ray is moving at the speed of light c. Again, we solve for T2. And we'll move our result over to put it with our first result. So the total time for one tick of our light clock we will call delta t. That's equal to t1 plus t2. You can put these over the same common denominator. The v's cancel, and the bottom, the denominator is c squared minus v squared. If we multiply top and bottom by 1 over c squared, we get 2L over c, like that. Now again, we want a relationship between L and L naught, and we don't want t involved. So we're going to substitute in for delta t using our time dilation expression. And then use the fact that delta t naught equals 2L naught over c. So this becomes 2L naught over c over 1 minus over c squared. So we now have two expressions for delta t. The first expression is derived using the horizontal light clock, and the second expression was derived with our time dilation calculation. So we're going to set this expression equal to that expression, since they're both equal to delta t. The 2 over c's cancel. And if we cross multiply by 1 minus v squared over c squared, we're almost there. So we find that the length L of the light clock viewed from the moving frame of reference equals L naught times the square root of 1 minus v squared over c squared. But we can identify 1 minus v squared over c squared as 1 over gamma. So we can also write this as L equals L naught over gamma. So in summary, length contraction is defined as the compression of objects along their direction of motion, as seen from a moving reference frame. So in the expression for length contraction, so L naught is the rest length of an object. L is the length of an object as seen from a moving reference frame. And V is the relative velocity between the two frames. Again, sometimes this is written as L equals L naught over gamma, where gamma is the dimensionless Lorentz or gamma factor. Let's look at a simple example where two people are in relative motion, Ms. Blue and Mr. Red. From Mr. Red's perspective, Ms. Blue is flying past him. She seems compressed along her direction of motion due to length contraction, and her clock is running more slowly than his. However, from Ms. Blue's perspective, Mr. Red also seems compressed along the direction of his motion, and his clock seems to run slow from her perspective. Both perspectives are correct. In relativity, there is no privileged position, no absolute frame of rest from which all other motions can be judged. All motion is relative. Up next, an experimental confirmation of special relativity involving cosmic ray muons.